The next double performance is about end stations and instruments, and will be given by Adrian Mancuso and James Green. Please. Go ahead.
Okay. Sorry, we've got another double act. I'm James Green. I'm from the Central Laser Facility and also work package lead for instruments on UK XFEL CDR process. And I'm going to be talking a bit about instruments and end stations, along with Adrian, who's the new Physical Sciences Director at Diamond, and also bringing his expertise from his time at his previous role at European XFEL. So just to talk briefly about sort of how we're going to go over this talk, start by some of the sort of broad design concepts that we're thinking about in terms of designing a suite of instruments for UK XFEL that can address all the various scientific challenges and broader science areas that you've just heard about in all the talks this morning. Then going to talk about some of the sort of what we think of the real highlight capabilities that can make a UK XFEL truly sort of leading next generation facility for all the current users and hopefully lots of future users as well, new to the field. I'm going to outline some of the aspects of secondary sources, a sort of world-leading tunable synchronized secondary source provision. I know Adrian is going to focus on some of the specifics to do with all the different sample environments that we're going to need, as well as all the high-speed large area detectors and sort of associated data, of course, that goes along with that. And then I'm going to wrap up with a few of the sort of next steps in this process over the next few months and years. But in terms of sort of instrument design, I should say that, I mean, a lot of this is aimed kind of at the sort of main concept of building a sort of dedicated UK XFEL facility, but a lot of this is obviously applicable for considering the other options in terms of facility upgrades as well. But all the sort of instruments that need to be designed for UK XFEL obviously need to primarily address the scientific challenges outlined in the UK XFEL science case, although this will obviously be an international facility in many contexts, so we're going to bear that in mind with the consultation process. But the aim is to combine all the new advances in XFEL beam delivery that's been talked a bit about with a lot of cutting edge capabilities across a range of different areas that are relevant for instruments and end stations. So that starts with things like X-ray beam transport, actually maintaining a high quality X-ray beam all the way from source through to sample, all the different conditions in terms of wavelength, pulse energy, sort of focusing conditions that people need. Looking at the different sample environments, so solid, liquids, gas, more extreme conditions, going along with the rep rate of the facility, of course. Secondary sources, I'm going to mention that a few times, but especially in terms of synchronization and tunability. And yes, high frame rate detectors, data collection, everything else. Luckily, again, there's already been mentioned in previous talk, but there's dedicated work package leaders for a lot of these areas. And as you can imagine, there's a lot of close interfaces with crossover between all of these. I'm just going to hand over to Adrian now for the next couple of slides so he can bring his expertise on what we need for a broad range of instruments.
Thanks, James. So as James pointed out, I'm relatively new to the UK community, but I've been made to feel really welcome since I've been here. So it's really great to have a chat with you today. So XFEL instruments are diverse, and we know this, many people in this room, and they look quite different. And I've used European XFEL examples because I could. And we see that these are really very vastly different capabilities to do a broad and interesting range of science. Makes it very hard to talk about end stations in a general sense, but that's what we're going to try and do. And some of the generalizations we think about are key questions. What should an ensemble, what should a good portfolio of XFEL end stations do? And the first thing is obvious. I like to say obvious things. Some people know that, just to support a diverse range of world-leading science. But also in this context, to uniquely exploit the properties of the source of this UK XFEL. One of the things that I'll come back to a number of times is the idea that we need to efficiently deliver those science outcomes. And what does it mean to do that in a large-scale facility without compromising the creativity that we need in science to do something new? And it's an enormous challenge, and it's incredibly interesting. It means we need all the right technologies, the optics, the sample, the detector, and we'll harp on about this a little bit. But it also means we need the appropriate complementary capabilities to fully exploit the machine, to fully exploit those end stations. That's everything from sample preparation labs for the different kinds of science we want to do, the appropriate tools to analyze data, but also the theoretical machinery to make sense of the data we collect, and much, much more. And this needs to be thought about at design rather than after the fact. And as I said before, while thinking about doing these things efficiently and ideally with high throughput and publishing lots of papers, we don't want to preclude the creativity. How do we design our facility and our end station such that we can still do this? So there's it's back to you, James.
I'll just expand on that a bit. I mean, like, because one of the first capabilities, luckily we've already heard a bit about it from so what Dave just mentioned, his talk there, but one of the interesting things I think that we can bring to this is to do with expanded instrument provision. We're not starting the design process from saying, right, we're going to sort of mimic what we see at LCLS2 or European XFEL. But of course, the science areas may be broadly similar, so some aspects may or may not be mirrored. But one option, it's already been discussed, is that if we have this high repetition rate megahertz capability, we have that option to deliver maybe 100 kilohertz, could be slower rep rate to multiple instruments simultaneously. And that only obviously, well, that could be seen, you could do it by, say, splitting a number of instruments into more dedicated end stations for more specific scientific setups, allowing to more rapid switch over between experiments, which obviously is just going to get you more sort of throughput in terms of users, but it also can have other benefits in terms of more consistent facility performance. If you're sort of ripping less out each experiment and reconfiguring each time, then you can imagine things being a bit more reliable, having less issues with timings, things like that. But then also the counter to that is what Adrian said, and that you still need to have room for that flexibility. You don't want to just have completely fixed end stations. So there's a balance to be had there, and I think that's really very good to have sort of feedback on people's views on that. In terms of instrument support, this is something I think that gets a bit overlooked, aside from the big headline capabilities, but I think the offline facilities and other associated operations are quite critical. They made a difference between a successful experiment and one that's not necessarily a failure, but maybe one that's a bit more inefficient in terms of how it's run. A lot of offline work is often done months in advance at different universities or the weeks before at some of the XFEL offline labs. A lot of this to do with sample assembly and preparation. Samples are often extremely precious, expensive. So you want to make sure you're confident in how they're characterized and how they're delivered on the experiment. And then sort of coupling on with that, it's about sample delivery. If you're having to swap samples all the time, you want to have your sample labs close and easy to reach from the actual end station itself. And then there's other stuff to do with secondary sources. If you do need to use a laser to pump your sample, can you get access to that in advance of your experiment to make sure you're confident of what you should be seeing on the experiment, ideally using the same laser you actually use on the experiment itself. And then also data analysis, of course, is critical. And again, that's already been mentioned about having the tools to mean that it's not just about acquiring the data and analyzing afterwards, getting to the point where you can do sort of quasi real-time analysis so you can tune the experiment as you go. But another sort of interesting discussion point related to this is about facility-led expertise. I know some groups pretty much pack a whole experiment up in a box, ship it around the world, do the experiment, ship it back again. But that's not exactly possible if you're a brand new user to doing XFEL science. So if we have a more facility-led sort of expertise model with centralized sort of sample environments, detectors, and sources, that does effectively lower the barrier to entry to new groups. But again, countering that, we've got to leave it flexible for sort of new technologies and applications to come in as well. So we're keen to get feedback from a lot of the users and other XFEL facilities on how they've been running things and how that's been. Secondary sources, so I won't spend too long on this slide because I know they've already mentioned it, but ultra-fast tunable laser systems are now pretty much standard for most experiments on all the various different instruments. And I think the user requirements have evolved a lot over the last sort of decade or so of operations. So it is something we want to build in from the start in terms of a broad range of laser wavelengths and, of course, having them more precisely synchronized to these hopefully transform limited pulses. And again, that question got raised in an earlier talk about, should these ideally be centralized? They could be distributed to multiple instruments depending on the experimental configuration if we're doing different science at different end stations. Or obviously, if things are really critical in terms of synchronization, it might be that some lasers are absolutely fixed, sort of rock solid to some instruments. So that will be an interesting question as to how that's laid out. Another thing, which I'm going to now focus on is, as David said, this could be a real selling point for a UK XFEL to exploit our leadership in this area, is provision of high power, high energy laser drivers for HED studies, but also other scientific areas as well through secondary source creation. Now, some of you might have already heard of diode, the sort of dipole laser technology that's developed at the CLF, but essentially this operates by using a sort of series of diode arrays that pump a number of thin cryogenically cooled ceramic laser amplifier slabs. And the nice idea about this technology is that it's very scalable in design. You can produce sort of high repetition rate, 10 hertz pulses of sort of nanosecond pulses of laser light in the infrared, from 10 joules up to 100 joules, and now a bit beyond that. It's very efficient in terms of you can convert it to green or UV wavelengths as well for different applications. And you can also get sort of quite nice temporal control of the laser pulse as well, which is often something people want to do. It's also a lot more efficient just sort of energy-wise as well. Sort of if you're talking about wall plug efficiency compared to conventional laser amplifier technology, it's a lot more efficient. There's actually already been 2 of these laser systems delivered and operational. So has already been mentioned, the D100X laser at the HED sort of high BEF end station at European XFEL has now been commissioned. I think the first user experiment's coming up in May. But also the dipole 100 system at high lays, as Emma mentioned as well. And that's already actually been demonstrated to operate at 145 joules continuously at 10 hertz for over an hour with, I think, 0.1% RMS stability. So very impressive sort of average power level now. But what's the big sort of selling point? I think looking at it from an XFEL perspective, I think the main thing is about the flexibility, and that if you have tens of joules up to 100 joules, maybe even kilojoules at multi-hertz repetition rate, it gives you an ideal platform for doing creating laser-driven shocks for dynamic compression experiments, as well as laser-driven sort of IFE research, as well as sort of on the industry side as well. It's an ideal platform for doing laser peening studies, and connecting in a bit with what David was saying in this industry talk. But also the nice thing is about it is that if you frequency double this dipole pulse, you then have an ideal pump for a petawatt class or multi-petawatt laser system. This in itself can be used to study relativistic laser matter interactions, fundamental physics, tying back to what Mel was saying. But these lasers themselves are also ideal sort of tunable secondary sources to create beams of X-rays, gamma rays, electron beams, protons, neutrons, most things you can think of. This can be considered as an ideal platform for looking at other methods of sort of future FEL platforms. So there's been some quite impressive progress in the last sort of year or so of using sort of GeV electron beams for a laser-driven FEL. And again, this can be, it's still very much early days, but something that's been promised for a while, but it's actually showing some decent progress at last. No one's saying that's going to be the sort of initial operating sort of background to a UK FEL, but it's something that we can have as an additional secondary source maybe in future. Also, these secondary sources can be used for themselves for a range of different scientific experiments, and also for industrial applications, which is a nice point just to insert just a quick slide on the Extreme Photonics Application Center at the CLF. So this is a new state-of-the-art diode pumped 10 hertz petawatt laser system coupled to 2 experimental areas, jointly funded by UKRI and MOD. And the main aim about this is that it's a new facility to sort of properly strategically develop, as well as doing fundamental science, tunable secondary sources for a range of applications. We've had a lot of work in terms of proof of principle work over the last 10, 20 years as to how lasers can generate these very interesting secondary sources with quite unique parameters. But this is the facility that's going to move that forward into sort of tunable, robust sources that can be applied across a range of different areas. And yes, we've got 2 experimental areas, one focusing more on using gas targets to produce sort of multi-GeV electron beams and X-ray sources, and one more on the looking at things like protons and neutron sources as well. So that's something that can be applied for a UK XFEL. So looking at sort of moving forward in the future with these dipole sources, we operate around here in terms of energy and rep rate in this sort of parameter regime. But going forward, people would like to see a lot more energy per pulse, and that may be possible at sort of multi-hertz capability. There's already plans to scale that up, and that can also be used for pumping multi-petawatt laser systems. If you want to really push the rep rate, that's possible as well, but it'll have to be at a sort of lower energy regime. But if you want to produce a lot of secondary sources for a certain scientific application, at a kilohertz, say, that might be a route forward for that. And there's also another regime, I think, that's kind of separate, and that some people want really multi-kilojoule laser systems to study the most extreme sort of pressures and densities. That's not likely at this stage to be dipole based unless you combine a lot of lasers coherently. Could get quite expensive, but there's other sort of routes there, looking at like cooled amplifier technology and things like that. But there's a lot of R&D challenges here, which I've highlighted. I won't talk through them now, but there's a lot to sort of work through to over the next 10 years to reach these points. But it'd be good to get feedback on what the real priority areas are. So I think I'm just going to hand back to Adrian. He's going to talk a bit more about the sample and detector side.
Thanks, James. So yeah, so we have thinking about samples, which is incredibly important, and a number of unique sample environments. And a really challenging strategic question for an XFEL is, well, which sample environments would we choose to support? We have the potential to have an enormous zoo of sample environments, and we need to think about that in a strategic way. So XFEL sample environments should ideally replace sample at the rate of the source for certain kinds of experiments. That could be very high. Should be readily usable by the user community, which is not true of some today, or at least not impossible to use. And they should be accessible, inexpensive, distributable for testing or otherwise accessible. And of course, we want to accommodate a wide variety of samples in a broad variety of states, but we can't do everything. And so you want them to be standard enough that you can do the experiments you want to do. And examples include things like liquid jets, megahertz rates here, gas injectors, fast scanning stages, diamond anvil cells, and more. And so there's a really interesting dialogue and discussion to be had about how do we optimize our use of what will be finite resource towards supporting samples, which will be critical for experiment success. The other thing that might be critical for experiment success is high-speed, large area detectors. And we know these are tricky as well. So detector technologies that are matched to the high repetition rate in particular are a key challenge. There's few, if any, really, that you could argue are commercially available technologies. And we should remember that there's a broad variety of science need. Some detectors will need to look at high dynamic range signals, other will be looking at single photon sensitivity, potentially at low photon energies. And these draw detector developments in different directions. And the same concept is true that in a finite resource environment, every detector will not be feasible. We need to be clever about our strategies about making sure we have the right detector solutions for the science cases that we're talking about. The other big facilities have detectors ongoing, and I wanted to remind mainly myself that there are other detectors rather than just the big 2D detectors. There are others as well for measuring all sorts of things which need to be considered in the design of end stations as well. But for a little bit of fun, this is the STFC delivered LPD at FXE at the European XFEL. It's about as tall as me, so it's almost a person high. I also want to thank the Royal Society for such an inclusive lectern. It's really the best lectern I've ever used. This is the Daisy and Partners Egypt being installed at MID some years back, and you see again the scale there for the people. So these are large bits of kit and need to be considered carefully. There are also significant investments over a long period of time to deliver the properties that are needed for these investments. And so a strategy around that becomes important. So we come to the fun summary slide. Shall I do this, James?
Yes, go ahead.
You happy with that? Okay. James did all the work, but I'll do the summary slide. So I think the most important word in that sentence is portfolio, a world-leading instrument portfolio to match the capabilities. You need a selection of instruments that exploit the capability of the facility. And that includes synchronized sources, it includes the samples, the detectors, it includes all of these supporting capabilities, analysis, theory, much more, thought of now before we get too far down the river so that we can exploit those capabilities well into the future. And of course, what's really fun, actually, particularly for me, is that the way we'll do this is enabled through talking with you, the community, and users all over the place to understand those challenges, understand R&D priorities, and go there. And then, of course, there's work with the team to draft this with input from all the stakeholders, etc. So all that remains for me to do is to thank you, because you will be contributing to this conversation. I want to particularly thank James because he made almost all the slides, and invite you to ask tough, nasty questions.
Okay, once again, I think the timing was excellent. I think this excellent chairman really is doing a great job, if I may say. So this leaves time for question, and we have one over there. Orville? Yep.
Alan Orville, Diamond Light Source. Luckily, you're physical sciences director and not life sciences director, so I can ask the tough question. the elephant in the room is, with a limited budget, how, as a community in this exercise, do we choose between all the various choices that are out there? There's far more science than we have money. What's a good strategy to work through? Do we come to consensus? I'm a middle child. I'm always trying to come to consensus. But there may be communities and external funding that really helps push, right? So peer review is really something we have to pay attention to. We don't take this lightly, and it is a very hard question. So I sort of bring this as a discussion point, but also as a reality check.
Yes, you want to take
It's certainly beyond my pay grade to comment too much, but I think the important first step is we're taking here today and in the ongoing processes of engaging with the community and genuinely understanding what the science needs are. The fun part and the hard part will be to understand synergies and opportunities to make the most of that first before we even talk about hard decisions. And I think it's what's really what inspires me about this project. It was a number of people this morning saying, we want to think about this from the science up. It's not a copy of somewhere else. We're not going down the same roads as before. We're thinking about the science and building this project up from the ground up. And so that approach is correct. And I'll leave the hard decisions to people more senior than me.
Okay, one more. Yes. Mike Dunn over there?
Yeah, it's Mike.
Thanks a lot. Mike Dunn, LCLS. I just like to make a comment and invite your reaction to it, in that if you look at, by analogy, where XFEL science is going, by analogy, say, to particle physics or astroparticle physics or astronomy, in those very mature communities, tens of % of the cost of a new project goes into the detector, the sample environment, that we would call it, and so forth, that you've been talking about here. And my own personal view is that that has to be true for the next generation of XFELs as well. Yet we spend most of our time concentrating on the source. But if you look at where we are today with LCLS2 and HE, I'll talk a bit more about this later, by far the most limiting factor is not the source, but our ability to refresh the sample or detect the photons. And almost certainly for a long, long time, the data acquisition and analysis system is far, far behind where it needs to be, by an order of magnitude or more. Yeah. So I wonder if you could comment on the degree to which, for this process going forwards and from the funding agency's point of view, there is this acceptance or realization or endorsement that some major fraction of this project should be vested not in the source, but in the other aspects of the science portfolio.
So I have to take my professional hat off and put my personal hat on, because I haven't been here long enough to understand the landscape. But the astute observer may have noticed by the choice of material presented that at least I think that is critical in terms of being able to deliver science outcomes. And having seen, the challenges of sample delivery at European XFEL up close, even in a field where that is focused and well-defined, it's clear we need to think about those things. The data challenge, it's the wrong way to think about it as a challenge. It's an enormous opportunity. What I didn't get a chance to talk to you about is the fact that these high repetition rate experiments produce so much data that enables a whole new way of thinking about stochastic processes. It's an enormous challenge, and we must meet that head on. So I'm super excited about these things, but I agree we need to think, and I think that's what's exciting about this project. We need to think in a novel way about what these facilities are, how they function, and how they operate. That's a whole other question for another day. But we have an enormous opportunity here because of where the UK XFEL is positioned in time with respect to the learnings of FELs that have come before.
Yeah, I agree. Can I make just one response? I think this is where, in terms of the differentiation of the options, greenfield versus, building on an existing site, there are really significant opportunities on that greenfield site to bake in the in situ data acquisition, the in situ sample environment. That is very hard to do, certainly at my facility. Yep. And I'm sure others.
Yeah, I'll defer to John.
Yeah, thanks, Mike. This is a response to what you're saying. Absolutely right. I think we're very conscious of the fact that to really be a next generation XFEL, it's not just about the X-rays, it's about all the other stuff that goes around it. And so, yeah, a greenfield site is definitely what we're thinking in terms of, and also phasing. You're not going to have everything on day one, but you might have everything after the 3rd or 5th phase. And I think that's the way we're thinking about this project. So it makes it more affordable at each phase, but obviously we need to bring in additional funders and sponsors, perhaps internationalize the project, and look for communities who are willing to work together to inject some of these very specialized resources. So absolutely, I think it's a great question, and it's one we need to be thinking about now, because if we do go ahead to build something, we're really going to have to get all the ducks lined up on all of those things well in advance. Thanks.
Well, actually, I mean, I also have a comment, if I may. This ratio of the cost of the source with respect to the cost of the other things, important things like detectors and the auxiliary sources, for instance, the lasers and so on. One way also to think about that is also to think that when we are talking about the physics of the 30s, the 40s, and the 50s, as we heard this morning, one might think that on this kind of time scale, one may abandon the paradigm of RF-driven accelerators. And if we have some promise from, say, Wakefield accelerators and other things like that, this could compress the cost of just the sheer size and civil engineering of XFEL, which is enormous, right? So thinking about very far ahead, one could also take this factor into account. Yes, we have there.
Sorry, at this point I have to step in. So Dave Newbold, STFC Director of Particle Physics. So I'm the guy who builds those things, which we're not going to build anymore. I think I just want to echo Mike's comment here. I mean, I think it really might be a brilliant idea to go and have a look at how the budget for the large facilities, so not just the capital budget, but also the operational budget actually breaks down. I mean, it does look radically different from how existing light sources work, and I think there probably are some lessons there. But coming back to your comment about future technologies, I completely agree. I mean, I'm not allowed to say this, so this is me, not STFC, but we may have built our last synchrotron, right, at any scale, and that leaves us with a little bit of a problem. I think if we don't build in that consideration to the design of any major new UK greenfield facility, so not only where does the technology development for other science fit in, but also actually how can that facility be reused in other purposes as well, then I think we're missing a trick. And I will be filling up your inboxes with that sentiment. So thank you.
Okay.